Now we're going to talk about improper integral of type 2. Okay, so we're type 1 and then we're type 2. I'm going to draw the graph so then you can actually visualize it. So you have a continuous function, okay? Say a continuous function like this, continue on A to B, but this over here, it has a vertical asymptote at B. So this function f over here, it is continuous on this interval. And you have a vertical asymptote over here. X equal to B, it is a vertical asymptote. Okay. So now we try to find this area under the curve right here. That will correspond to an improper integral, because this one here actually keep on continue going over. Is there's an infinite strip, right? Infinite strip, continue forever. Okay, so this area over here correspond to this improper integral. It's the integral of this function. X go from A to B. Now, at first you look at this, it seems like, well, is this a proper integral? But it is not. It is not proper, because when over here, f of x is going to go to infinity over here, close when you get close to b. Okay, so it is improper integral of type 2, but this type is more hidden. It's not that obvious. Okay, so it has a discontinuity over here at b, and the function go up to infinity. Okay. So it is improper integral of type 2. So we're going to define this. Okay, so define that similarly like before. So we're going to replace this part that is causing the trouble over here, the b over here, by t, where t over here will be represent any real number that is less between a and b. Okay, so less than b. Okay, and now that will be a proper integral because the discontinuity is only at b over here. Okay, so that will be a proper integral. And then you take this proper integral. So you can imagine this t over here is a number that is between a and b. And then now you let the t here go to b. So we're going to take the limit and let this t over here and closer to b from the left side. Okay, so you take the limit here and you let t goes to b, but remember this is from the left side, from the left. So we define this improper integral here as the limit of those proper integral here, where t goes to this b over here from the left side. Okay, now this, so providing that if this limit here exists as a finite number, and then we will say this is convergent, right? Okay, if this limit exists, when I say exists, that means exists as a finite number. So that was the first, so that's one, so this is an improper integral, okay? But this is the first case, okay? So I'm going to label that this is the first case. So this is case A. Now another case over here will be kind of similar. This time, instead that you have this vertical asymptote here at B, you could have a vertical asymptote at A. So I'm going to draw this. Okay. So over here at A, you have a vertical asymptote. So x equal to A, it is a vertical asymptote. And so the function will be like this. And this area under this. Okay, so this right here. It is improper. Okay, so correspond to an improper integral. Correspond to this integral. So we'll have go from A to B, f of x dx. We're going to define that similarly. Okay, so what do you think? So how do we define that? As the limit of, now we're going to replace this a over here by t, and then we're going to let this t here go to a from which side?
Left.
Left or right? Let's think. So t will be a number that is between a and b. So t goes to a from the
Right.
right side. Okay. So from the right side over here. Okay. Okay. So this is another case. The last case here, case C. This time you have this vertical asymptote between A and B. Okay. So we have this. So let's say it's C. So x equals C is a vertical asymptote. Okay. And then over here you have this A here and B over here. Then the graph over here. Okay, like that. Now, so that is correspond to this integral. So the integral from A to B, it is an improper integral. Okay, because this we have a vertical asymptote somewhere over here between A and B. Okay, improper. So the way that you can tell is that a discontinuity over here? Okay, is there any vertical asymptote over here in between this upper and lower limit over here? Okay. So how do we do this? Similarly, just like the other type, right? We split it into two integral. Okay. So we're going to break it into this two integral, the sum of this two integral. Okay. So go from A to C, and then here go from C to B. Okay. Now, and then for this one and this one, then you can just represent them by those definition above, right? Okay. Now, this integral, just like before, this integral here is convergent, providing that both this integral and this integral are convergent. So if one of them is divergent, then you conclude that this integral is divergent. Okay. Divergent means the integral here doesn't equal to a finite number. Okay. So this, it is convergent, providing that both this integral and this integral are convergent. So if you can find one of them is divergent, then you don't need to do the other one. Then we would just say this whole integral here is divergent. Okay. Okay. Now
I have
let's
a question.
go ahead.
Is that supposed to be a limit statement on case C? Can you break it up for the limits of those integrals?
Yes. Thank you for the question. So once I break it into this, then this one here, you will have this as the limit of like this type, this one. So the next step over here, this one over here, this part over here, this part over here, we represent this way. It's the limit of this proper integral. So that will be the next step. Because this part, after this part right here, you represent this improper integral here by this first one, this first case right here, right? Because it's of this.
Okay, that makes sense.
Okay, maybe I'll write it down here. Now this one here will be the limit, and then you go from A to T, and then f of x dx. Now T over here will go to C, from which side? From the left side, right? Okay. And then now this one over here, you can represent this by this limit of this proper integral. Okay, and then here will be T to B, and then you take this limit, and then T goes to C from the right side. Okay, from the right side, right here. Okay, then yeah. So after you break it into this, then you can deal with them using those definitions, the two separate definitions right here, right? Okay. Okay. Now this example, the next example, we're trying to find this integral. Now at first you don't see anything suspicious, right? So what is a normal integral? It's actually improper integral of type 2. Why is that? Can someone tell me why is that improper?
Because 1 over cosine of pi over 2 is equal to 1 over 0.
Yeah, you got it. Okay. So for secant, okay, so it is a reciprocal of cosine when x equal to power 2, cosine is equal to 0. So what happened over here it is, so secant x being the reciprocal that will go to, depends on where you go to infinity. Depends on where you go to power 2. If we go to power 2 from the left side, okay, then it go to positive infinity. So the graph for secant of x, this is for secant of x. Okay, so it go to positive infinity right here. Okay, so this one here corresponds to this area under the curve right here. This right here. So this stripe right here is actually going. It's an infinite stripe. Okay, continue going up. Okay, like this. So it's improper. Okay, you have a vertical asymptote here at when x equal power 2. Okay, so we're going to use the definition. Okay, so we're going to replace this power 2 here by t, where t is represent any real number that is between 0 and power 2, between this lower and upper limit. Okay, and then that will be proper. Okay, and then we let t go to power 2 from which side? From the left side. Okay, so t will go to power 2 from the left side. Now I want to see any of you remember what's anti-duality of secant of x. Do you guys remember? You guys remember? Okay, it is ln of what?
Secant x plus tangent x.
Yes, you got it. Okay, the absolute value of secant x plus tangent x. Okay, and x over here go from 0 to t. Now that is equal to, now t go to power 2 from the left side. Okay, and now you just substitute, right? Okay, now okay. First, I want to ask you guys, what is secant of 0? Secant of 0, it is what? It's 1, okay? Tangent of 0 is 0, okay? And what's ln of 1?
0.
Yes, you got it. So ln of 1 here, it is equal to 0, okay? So that's equal to 0, okay? And then what about this part right here? For this part over here, when t go to power 2 from the left side, okay? So let's see what happened. You see, here's the graph for secant of x, right? So when t go to power 2 from the left side, what happened to secant of x? It goes to what? What happened?
Infinity.
You go to positive infinity, right? So that goes to positive infinity. And then what happened to tangent? Tangent will also go to infinity if you look at the graph for tangent, okay? So that will also go to infinity, positive infinity, okay? So this part over here, you're taking ln of a quantity that go to positive infinity, then that will also go to infinity, okay? So this whole thing over here, this whole over here, it goes to positive infinity, okay? So this integral here, we found that is positive infinity, which is not a finite number. So convergent or divergent?
Divergent.
Yeah, so it is divergent. It diverges to positive infinity. Okay, all right. So I'm going to stop here. I probably make a video to cover the rest of this for this section right here. And then after that, you guys will have a test on the other side. Okay, we're gonna make a test for that. Okay, are you guys good? So today we cover improper integral of type 1 and also type 2. Okay, so we finished type 1 and then we talk about type 2.